Hello, my name's Margaret, and today I'm going to be helping you with a problem from Chemistry, the Molecular Nature of Matter and Change. This is Chapter 8, problem number 5, and it's asking to summarize the rules for the allowable values for the quantum numbers of an electron in an atom. And really quick, I want to go over kind of where these values come from, or just where quantum numbers come from in general, because I think that it's important to understand these, and I think it's sometimes challenging to understand the concepts of orbitals and things like that in general. So really quickly, so going all the way back, the basic idea is that this guy named Schrödinger decided that he was going to try and describe how particles moved around and interacted with each other. And so he decided he was going to start out with the laws we already had. And so he took Newton's laws and regular physics laws, force is equal to mass times acceleration, all those normal types of things that you learned in physics, and he shrank them down to the microscopic scale and did a bunch of math, and then he came up with the Schrödinger equation. And he found out that things don't quite behave the normal way they do at the microscopic scale versus the macroscopic scale. And then he did a bunch more math after that. And then what we ended up learning as we did more and more math to figure out, what other differences there were in the microscopic scale, and to finish trying to solve these equations absolutely, is that they can't be fully solved, first of all. And so we have to use probabilities instead. And the biggest thing that came out of this, especially in pertaining to this chapter and the chapter previously with 7, is that electrons have to be described by several different equations in order to take their particle and wave-like properties into account. And more specifically, orbitals are essentially a map of where a specific electron or electron pair are likely to be around the nucleus, all right? So the atomic orbital is described by the first 3 quantum numbers, which again is the probability of where it's supposed to be, and then the spin of the electron is described by the last quantum number. Now, this is in particular something to understand, and the reason I wanted to clarify this to you is because you end up seeing the term radial probability quite a bit throughout the last chapter and this one, and you see these types of graphs quite a bit as well. And essentially what they're doing is R right here is the distance from the nucleus where all the protons are located, and this right here is the probability of finding an electron in a position from the nucleus. And so as if you see the as this graph gets higher, you find the probability getting larger of finding an electron there. And so for this graph right here, if we were graphing the 1s orbital, you see that really close to the center of the atom, it shoots up really high, and then it drops really frequently, and then it goes down to almost 0 for the entire rest of the graph. And so when you end up plotting that in 3 dimensions, that's how you end up with the s orbital looking like this big round ball. And so when you do that over and over again for all the different orbitals and all of their different equations, that's how you end up with the different orbital shapes. So moving forward, we have our 4 different quantum numbers here. So the principal quantum number is it's a positive integer described by the letter n. A positive integer. So that means that n is equal to 1, 2, 3, and it goes on hypothetically forever. And it is describing the relative size of the orbital. And based on what we know about these types of graphs over here, we know that it's also telling us the relative as well, the relative distance. On the radial distribution plot. So if we looked at this and we had, n is equal to 1 right here, and we had, n is equal to 2 would be shifted slightly that way, and we could have n is equal to 3 slightly that way. That's something we know based on the principal quantum number. So moving on, the angular momentum quantum number is denoted by the letter L. And this is an integer. And this is from 0 to n minus 1. And this tells us the shape of the orbital. So if we had n was equal to 1, then we know that L is equal to 0. If we had n is equal to 2, then we know that L is equal to 0, 1. And then if we had n is equal to 3, then we know that L is equal to 0, 1, 2. So the magnetic quantum number is denoted by m sub L. And this one is an integer from negative L through 0 to positive L. And this gives us the 3D orientation around the nucleus. And when it says 3D orientation, it means in space. So when we're talking about the X, Y, and Z axis, so it's talking about exactly which planes these would go in. And so m sub L is equal to 2L plus 1. So if L is equal to 1, then M sub L is equal to -1, 0, and positive 1. And this is talking about the number of terms. Let's get some division here. The last one is spin, which is denoted by M sub S. It's got two values, +1/2, -1/2. And this is the electron field. And this is where, we talk about when they're pairing off up or down.